welcome to this lecture. In this lecture we continue our discussion of regular singular point, and if you recall, in previous lecture we have discussed the case when the roots of the initial equations differ by an integer, and as an example we have taken the Bessel's equation of order 1 by 2, and we have seen that the equation is this t square y double dash plus t y dash plus t square minus 1 by 4 y equal to 0. So, this is an Bessel equation of order 1 by 2, and we have already checked that here t equal to 0 is a regular singular point, and we have also seen that the roots of the initial equation is given by r1 equal to half and r2 equal to minus half, and here we can say that r1 minus r2 is equal to 1. So, it means that this case falls in the category when the roots of the initial equation differ by an integer, and we also have calculated the coefficient corresponding to r1 equal to half, that is a2 and half equal to minus 1 to power n divided by factorial 2n plus 1, and here please note down that your initial equation is given as f of r equal to r square minus 1 by 4, for by which we have calculated the roots of the initial equation, that is 1 by 2 and minus 1 by 2. And we also seen that if you look at the coefficient of t to the power n plus r in general theory, we have already seen that f of n plus r a n equal to minus k equal to 0 to n minus 1 k plus r p n minus k plus q n minus k into a k. So, here we have seen that if for some let us say take r2 as r1 is bigger than r2, and if you take the case corresponding to r2 and that r1 minus r2 is differ by some integer, let us say n naught, then this for n equal to n naught, this is what f of n naught plus r to a n naught is equal to minus summation k equal to 0 to n naught minus 1 k plus r p n naught minus k plus q n naught minus k, this is capital and a k. Now, here we already know that this n naught plus r2 is r1, and r1 is a root of this polynomial f of r. So, it means that this is going to be 0. So, a n naught 0 into a n naught equal to this quantity. Now, if this quantity is non-zero, then we do not have any solution, we do not have any possibility to find out this a n naught, and hence we can say that we do not have any series solution of the form of Frobenius. But if this part is 0, if the right hand part is 0, then we can take any value of this a n naught, and in particular we take a value of a n naught is equal to 0 and to find out the other solution. So, in this particular case your n naught is basically 1. So, a n naught equal to 1. So, here we look at the corresponding equation for this. The corresponding equation is f of 1 plus r a1 equal to 0. So, here it is quite easy to see that right hand side is already 0. So, this right hand side is already 0, and if you look at the values of f of 1 plus r, that is 1 plus r whole square minus 1 by 4 a1 equal to 0. Now, if you put r2 as 1 by minus 1 by 2, then it is what it is automatically 0. So, it is 0 a1 equal to 0. So, it is in this particular problem this right hand side is already 0. So, this right hand side is already 0 in this particular example. So, here I can take value of a1 as any value, in particular I am taking the value of a1 as 0. So, it means that here we have the second series solution in the form of Frobenius form. So, let us continue our study. So, here we take r2 equal to minus 1 by 2, and we set a2 equal to 1, and we say that equation 2 is automatically satisfied, and you can take any value of a1 and we will set a1 equal to 0. If we take any non-zero value, then this I am leaving it to you, that if you take a1 as any non-zero value, let us say that a1 is equal to 1 for example, or a1 equal to alpha, if you take it, and then you do all this calculation, and at the end you will see that y2, the second solution which we are trying to find out corresponding to r2 equal to minus half, will contain a part of y1. So that I am leaving it to you. So here now let us find out the solution corresponding to r2 equal to minus half, and here we have seen that here the problem which we are discussing is not occurring, because here the right hand side is already 0. So I can choose any value of a1, and we have taken a1 equal to 0, and since a1 equal to 0, and by the recurrence relation we can simply say that all the odd terms are 0. Look at the recurrence relation, an is equal to minus an minus 2 divided by n minus half whole square minus 1 by 4, and we can simplify a square minus b square, and we can write n minus 1 by 2 plus 1 by 2, that is n, and n minus 1 by 2 minus 1 by 2, that is n minus 1. So we can write an as minus an minus 2 divided by n into n minus 1, that is for r2 equal to minus half. So we can calculate a2 as minus a naught upon 2 into 1, and a naught is 1, so it is minus 1 upon factorial 2, a4 as minus a2 upon 4 3. So a2 is, we have already calculated this, so a4 is 1 upon factor 4, and so on. So we can calculate that a2n is equal to minus 1 to power n upon 2 to power factorial 2n. So we can say that by induction we can say that a2n is equal to minus 1 to power n divided by factorial 2n. Now corresponding to this, we try to find out the solution as y2t equal to root t. Here it is what, y2t is equal to t to power say r2 summation a n t to power n, n is from 0 to infinity. So r2 is minus half, and a n we have already calculated, a2n as minus 1 to power n factorial 2n, a2n plus 1 is simply 0. So we can write it y2t as 1 upon root t, because t to power minus half is 1 upon root t, and a2n a0 is 1, so 1 minus a2 is sorry, t square upon factorial 2, a4 is what, t to power 4 upon factorial 4, a4 is basically 1 upon factorial 4, and a6 is going to be minus 1 upon factorial 6, t to power 6, and so on. So if you look at, this is 1 upon root t, and in the bracket it is this term. So this is what, this is the formula of cos of t. So y2t is written as 1 upon root t cos of t, and this is our second solution of Bessel's equation of order half. And we can write down the general solution, and we can write down general solution yt as c1 1 upon root t sin t, and c2 1 upon root t cos of t. So this is our general solution of Bessel's equation of order 2. Now so far we have discussed the case of regular singular point, and we have seen that in case of regular singular point, our possible solution is given in terms of summation a n t to power n plus r, and we by taking this as a solution, we are plugging the value of y dash, y double dash into the equation, and with the help of the equation we try to find out an initial equation from which we can find out the roots of the initial equation, and we try to find out the coefficient with the help of recurrence relation. That we have already done. Now question comes that what happen if we have a singular point but it is not a regular singular point. Then our question is, can we apply the same method for which we have applied for regular singular point. So we are going to discuss two example which shows that to a certain extent we can do so, but not always. So it means that that's why our method which we have already discussed is valid or working very good in the sense of regular singular point, but in case of irregular singular point we may not guarantee that our solution work or not. So let us consider the differential equation x double dash plus p divided by t to power b x dash plus q tc x equal to 0. Here our unknown variable is x and independent variable is t. So here we are writing our equation like this xt. So here p and q are non-zero real numbers and b and c are positive integers, and x equal to 0 is an irregular singular point if b is greater than 1 or c is greater than 2. So we can first of all we can already check that t equal to 0 is a singular point, because the coefficient of x dash and coefficient of x are not continuous at t equal to 0. And then we want to check whether it is a regular singular point or not. But if you take b is greater than 1 or say c is greater than 2, then we can check that the coefficient means t into p by t to power b and t square q upon t to power c may not be analytic function if b is greater than 1 and c is greater than 2 or c is greater than 2. So either in each of these two cases we simply say that x equal to t equal to 0 is not a irregular singular point. So here let us say that that is already written here, that t equal to 0 is a singular point because pt equal to p upon t to power p and qt equal to q upon t to power c are not continuous at equal to 0. And also in the case of b equal to 1 and c equal to 2, that is the case which we have already discussed. And we say that in case when b equal to 1 and c equal to 2, this the singular point t equal to 0 is a regular singular point, as both tpt and t square qt are analytic function. But in particular if we take any value for b which is greater than 1, let us say b equal to 2 and let us say c equal to 3 value, and we try to show that in this case your we will get one Frobenius series solution. So for that let us assume that solution is given as xt equal to n equal to 0 to infinity a n t to the power n plus r. So here I am assuming that let us see whether this solution will work for this equation or not. We already know that for b equal to 2 and c equal to 3 your t equal to 0 is not a regular singular point. So let us see whether it will work or not. For x dash t you calculate and x double dash t you calculate, and that is summation n equal to 0 to infinity n plus r a n t to power n plus r minus 1, and x double dash t is n equal to 0 to infinity n plus r into n plus r minus 1 a n t to power n plus r minus 2. Now plug it back. So when you plug it back, you have n equal to 0 to infinity n plus r into n plus r minus 1 a n t to power n plus r minus 2 plus n equal to 0 to infinity b into n plus r a n, and here it is what, here we are assuming that b is equal to 2 here, then it will give you a n t to power n plus r minus 3, and in last term it is n equal to 0 to infinity q a n t to power n plus r minus 3. So here I am assuming that here c is equal to 3. So using this we have this term. Now just collect all the term and we write this as look at the term of t to power r minus 3 here, then here we have this term, and this term will give you the coefficient of t to power r minus 3, and that is corresponding to n equal to 0. So that is what p r, so p r plus q a naught into t to power r minus 3 is given when n equal to 0. But when you put n equal to 1, then this will give you the term t to power n plus r minus the t to power r minus 2. So it means that then this term will also come into picture. So it means that when you start from n equal to 1 to infinity, then this will give you what? This will give you n plus r minus 1 into n plus r minus 2 a n minus 1. So this I am writing, okay, let us say take the coefficient of t to power n plus r minus 0. So here t to power n plus r minus 3 will come when you take n equal to say minus 1. So here we write n plus r minus 1 into n plus r minus 2 a n minus 1 plus p n plus r q a n. So basically what we are doing, we are just first calculating the coefficient of t to power r minus 3, that we can take it from this term as well as this term. Now we want to write a general term. let us say that general term is t to the power n plus r minus 3. So, these two term is already given in terms of t to the power n plus r minus 3. So, p n plus r plus q into a n, that is already coefficient of t to the power n plus r minus 3. And if you look at from this term, if you want to calculate the coefficient of t to the power n plus r minus 3, then you simply replace n by n minus 1. When you replace n by n minus 1 in this, then you will get here n equal to 1 to infinity n plus r minus 1 into n plus r minus 2 a n minus 1. So, from this you are getting this term. So, it means that now we have we simplify like this. Now, equating the sums of like power of t equal to 0. So, first let us say t to the power r minus 3, and we have p r plus q into a naught equal to 0, and then you write t to the power n plus r minus 3, and that is valid when n is greater than or equal to 1. So, here when you put, then we have n plus r minus 1, n plus r minus 2, a n minus 1 plus p n plus r plus q a n equal to 0 here. So, from this in the first equation you can get your initial equation as p r plus q equal to 0, and we can simply say that here, since it is a linear equation, we will have only one solution, that is r equal to minus q by p as your one root of initial equation. So, here please look at here, since it is an irregular singular point, then only we can say that here we are getting only one root of initial equation. In fact, here initial equation is not a quadratic equation, it is a simple linear equation. So, here one root we have obtained as r equal to minus q by p. Now, according from this we try to calculate all other coefficients. So, a1 is basically what? So, here to calculate a1, let us look at here. So, here when you put n equal to 0 n equal to 1, then you will get a1 in terms of a naught. So, use the second and put n equal to 1. So, when you put n equal to 1, it is what? P 1 plus r plus q a1. So, that is what, let me write it here. So, here we put n equal to 1 here, then what you will get? It is r minus 1 a naught plus p and 1 plus r plus q a1 equal to 0. So, you can calculate your a1 like this. So, a1 is coming out to be this value. So, a1 is going to be what? Here this is a naught into r minus 1, r into r minus 1 plus, here we have 1 plus r p plus q a naught equal to 0. So, here you can get, this is a1, sorry. So, a1 is equal to minus r into r minus 1 a naught divided by this quantity 1 plus r p plus q, that we have already seen, that it is this here. Now, let us use that value of r as minus q by p. So, this using r equal to minus q by p, then 1 plus r is going to be p minus q upon p. So, using this we can write this as a1 as minus r into r minus 1 a naught divided by 1, so it is p minus q plus q. So, we can cancel out. So, we can write a1 as minus r minus 1 r divided by p into a naught. So, a1 is calculated, and similarly you can calculate your a2 and so on. So, he can calculate all the coefficient using your reconciliation 2 here, and we can say that our solution is calculated like this: a n is equal to minus 1 to power n r minus 1 r square r plus 1 whole and so on, and p to power n factorial n, that is n is greater than or equal to 1 here. So, we can write down our solution as y t as summation n equal to 0 to infinity a n t to power n plus r, and r is given as minus p by q. So, even if here t equal to 0 is your singular point, not only singular point, it is irregular singular point, but still we are able to find out a series solution. In fact, Frobenius series solution of the form Frobenius series solution in case of irregular singular point. So, here since t is equal to 0 is a weak weak irregular singular point, then we can find out one solution of this form. We are not able to find out the second solution of the form of Frobenius series solution. So, how to find out the second series solution? That for that you can use your variation of parameter method or any given method. So, here in this case we have seen that one solution we can obtain. Now, let us now I am leaving it to you that here I am assuming that your B is equal to 2 and C equal to 3. Now, I simply say that if you take B equal to 3 and C equal to 4, in that case you will not have any solution of the form of Frobenius series. That I am leaving it to you, that check that when case B equal to 3 and C equal to 4, we do not have any solution of the form of Frobenius series. Of course, it will have a solution, but not of the form of Frobenius series solution. So, here we simply say that here t equal to 0 is a weak irregular singular point of this differential equation. Now, let us consider one more example, and example is this. Let me okay here. Now, we already know that for B equal to 1 and C equal to 2, your differential equation is reduced to this, and that is your x double dash plus p by t x dash plus q by t square x equal to 0. If you look at, this is nothing but your Cauchy-Euler equation, right. This is a simple Cauchy-Euler equation, and we can simply say that here also if you want to apply your solution x t equal to n from 0 to infinity a n t to power n plus r, and similarly calculating x dash t x double dash t, we can simply say that L x equal to what, n equal to 0 to infinity n plus r into n plus r minus 1 a n t to power n plus r minus 2 plus n equal to 0 to infinity p n plus r a n t to power n plus r minus 2 plus q equal to 0 to infinity q a n t power n plus r minus 2, and if you calculate, coefficient will be what, n equal to 0 to infinity n plus r minus 1 plus p n plus r plus q into a n t to power n plus r minus 2. So, here we say that here when you start from n equal to 0, your all terms will come into picture. So, equating the sums of like power of t equal to 0, we will get this term. So, this is your general term. So, here we write f of n plus r a n t to power n plus r is equal to 0. So, here f n plus r is given by n plus r into n plus r minus 1 plus p n plus r plus q equal to 0 here, and we can simply say that here your this initial equation, when you put n equal to 0, your initial equation is what, this initial equation is a quadratic initial equation, and this will give you two roots of initial equation, and we with the help of two roots we can find out two solution of the one solution is given surely in terms of Frobenius series solution, and the other you can get depending on the cases. But here if you look at, this is a simple Cauchy-Euler equation, and we can simply say that if you remember, if you put n equal to 0 here, then it is what, r into r minus 1 plus p r plus q equal to 0, and it is the initial equation which you have obtained for Cauchy-Euler equation. So, we simply say that Cauchy-Euler equation is a simplest case of irregular singular point, and we can use the method to find out the solution for Cauchy-Euler equation, and we have already seen that t to the power r1 and t to the power r2 by suitably defining r1 and r2 we can get our solution like this. Now, look at one more example, and here also if you look at example is what, t square y double dash plus 3t minus 1 y dash plus y equal to 0. If you look at here also, t equal to 0 is a singular point. So, because here pt is what, pt is your 3t minus 1 divided by t square, and qt is what, qt is 1 upon t square. So, we will simply say that pt and qt are not continuous. So, t equal to 0 is a singular point. Now, just look at whether it is a regular singular point or not. So, look at tpt. So, tpt is coming out to be 3t minus 1 divided by t or you can say 3 minus 1 by t, and you say that this is not a analytic function. So, it means that here this TPT fails to be analytical. So, it means that t equal to 0 is a case of irregular singular point, right. So, if it is a irregular singular point, and still if we want to find out that whether the method which is given for regular singular point will work for this or not, let us assume our solution yt as summation n equal to 0 to infinity a n t to the power n plus r, and just calculate the y dash, y double dash and so on, and put it back to equation. What you will see, it is n equal to 0 to infinity n plus r minus 1 a n t to the power n plus r plus summation n equal to 0 to infinity 3 t minus 1 n plus r a n t to the power n plus r minus 1 plus summation n equal to 0 to infinity a n t to the power n plus r. Now, here if you simplify, you will get what? So, here let us calculate the coefficient of t to the power n plus r. So, here this term and this term will contribute in t to the power n plus r, and this will give a term of like if you multiply 3t into this, then it will also contribute in t to the power n plus r, and if you look at this term, will simply say the term of t to the power n plus r minus 1. So, so your term when you put n equal to 0, then this will give you so let us say let me write it n equal to 0 here, then corresponding to this you will get minus r a naught and t to the power r minus 1, which I am writing here. So, this is the term which we obtain by putting n equal to 0 in this second term, and then when you put n equal to 1 and onward, then all other term will also contribute, and we say that in general if we look at the coefficient of t to the power n plus r minus 1, then from first term if we get t to the power n plus r minus 1, if we replace n by n minus 1, then it is what? N, let me write it here. So, we are just want to calculate t to the power n plus r minus 1. So, first term will give you what? N plus r minus 1 into n plus r minus 2. I am replacing n by n minus 1 into a n minus 1, fine, and in second from this I can write 3, and it is what? N plus r minus 1, and again a 1 I am writing because of this thing, because this will not give a term like this. So, here we will get like this is a 1 plus, if you multiply minus here, then what you will get? It is n plus r just a minute, here it is a n minus 1, in last, from last you will get a n minus 1, and if you just calculate, here it is a n minus 1, and if you calculate, this is what you write this as what? N plus r minus 1, you take it out, then it is what? N plus r minus 2 plus 3. So, we will get n plus r plus 1. Then there is one more term left out because of this, that is here I have to write one more term, that is here minus n plus r a n. So, that I am writing here. So, we will get n plus r minus 1 plus n plus r plus 1 a n minus 1 minus n plus r a n, and these are the coefficient of t to the power n plus r minus 1, which I am writing here. So, it is, if you simplify, it is what? Okay. So, here we are calculating the coefficient of t to the power n plus r minus 1. So, one term we are getting from this by replacing n by n minus 1, that is n plus r minus 1 into n plus r minus 2 into a n minus 1. Here we are getting a term from this, then here 3 n plus r minus 1 a n minus 1. So, writing 3 n plus r minus 1 a n minus 1, and 1 we are getting from here when we replace n by n minus. So, here we are writing a n minus 1, and the term corresponding to t to the power n plus r minus 1 we are getting from this, then we are getting minus n plus r a n, and when you simplify n plus r minus 1 into n plus r minus 2 plus 3 n plus r minus 1 plus 1, and we write it like this. So n plus r minus 1 into n plus r plus 1 plus 1 into a n minus 1 minus n plus r a n into t to the power n plus r minus 1. When you simplify this, you will get what? N plus r whole square minus 1 plus 1. So it is n plus r whole square a n minus 1 minus n plus r a n t to the power n plus r minus 1 when we start from n equal to 1 to infinity. And then because you are replacing n by n minus 1. So n minus 1 equal to 0 means n is starting from 1 onward. So it means that here we have the lowest degree term is t to the power r minus 1. So equating the lowest degree term t to the power r minus 1 is 0. So we will get r a naught equal to 0, and then you write n to the power n r minus 1. So equating the coefficient of t to the power n plus r minus 1, we are getting this recurrence relation, that is n plus r whole square a n minus 1 minus n plus r a n equal to 0, that is for n greater than equal to 0. So if you look at the first equation, a naught cannot be 0, so r has to be 0. So this will again give you a linear initial equation, and here you will get only one root of initial equation, that is r equal to 0. So here we have r equal to 0. Now we, with the help of this root of this initial equation, we try to find out others a n. So you can simply say that a n is equal to what? A n is equal to n plus r a n minus 1. So here you have a n as n plus r, you can cancel out because n is positive, r is 0. So you can cancel out n plus r. So a n is given as n plus r a n minus 1 and r is equal to 0. So a n is equal to n a n minus 1. So here if you start, since n is greater than equal to 1, so let us start with n equal to 1 itself. So a 1 is equal to a naught, that we have listed here, and using this a 2 is what? A 2 is equal to n equal to 2, so 2 into a 1. So it is 2 into a 1, that is 2 into a naught. Similarly a 3 is what? 3 into a 2, and a 2 is 2 into a 2. So we can write it that a 3 is given as factorial 3 a naught, and we can use mathematical induction to show that a n is given as factorial n a naught and n is greater than equal to 2. So hence general solution we can write it as y t equal to n equal to 0 to infinity a n t to the power n plus r, that is n equal to 0 to infinity factorial n t to the power n. So here theoretically we can say that it looks that we got a solution, and solution is given by n equal to 0 to infinity factorial n t to the power n. But if you have already seen the theory of power series, that this power series has 0 radius of convergence, that you can calculate using your tools, that you can find out that radius of convergence is coming out to be 0. So it means that this power series is actually not a power series because it will never converge, it will converge only the point at t equal to 0. So it means that this is not a valid solution at t equal to 0. So it means that here we have seen that though it looks that our solution work out very fine and we are getting a solution, but actually this series solution is having radius of convergence as 0. It means that this is not a series solution of this equation, and here we can say that here t equal to 0 is a irregular singular point, but still but we are not getting a single series solution of the form of Frobenius series. But in previous example, though t equal to 0 is your irregular singular point, but still we are able to find out one series solution of the form of Frobenius form. So here we say that t equal to 0 is a strong, or say a strong irregular singular point. So that we want to convey that when point is not a regular singular point, that we may not guarantee that a series solution exist or not, because in first case we have seen that series solution exists and it is given by form which we have already discussed. But here in second case your t equal to 0 is a irregular singular point, but here your solution you can say that it is looks like that it is a given as a Frobenius series form, but actually it has no radius of convergence. So we simply say that it is not a Frobenius series solution. So it means that in case of irregular singular point, our method of assuming the solution as Frobenius series form may not work at all. So, here we want to give a message that when we have a regular singular point, then we can find out our solution using Frobenius series solution, but if it is not a regular singular point, then we have several other methods to find out solution, but this Frobenius series solution may not work. So, with this I conclude the study of Frobenius series solution method of linear second order differential equation. So, we'll thank you for listening us. Thank you.